All right. So I said that we've got an idea down. We're trying to start developing some notation. One of the reasons why I had to get very careful in our enumeration notation is because soon we're not going to be looking at any pictures at all. Okay? We're going to be doing this without looking at pictures at all, so we've got to be even more careful with the way we write things out. My next goal is to introduce something called summation notation. Okay? Usually about 2/3 of the students have seen summation notation. How many of you have seen summation notation? Yeah. Okay. So happy. Okay. I wish you hadn't, but that's okay. We'll start. I'm going to treat this as we're starting from scratch because that's the best place to start. All right. This is whenever you find yourself writing out a long summand, meaning a long expression with several terms separated by addition. Okay, if there is a pattern to how you're getting those terms, you could express it in summation notation. Okay? In my opinion, if ever you find yourself writing a ... it probably means you could shortcut it by writing summation notation. Okay? So we're going to learn how to do this. All right, the first thing is the letter that shows up here. Okay? This is the Greek letter sigma. Okay? Everybody does it to varying degrees of awfulness. That's about the best you'll see me do it. Okay? Everyone does their own sigma. It's worth practicing just a little bit. Don't spend too much time on it. Okay? But practice just a little bit making your sigmas. You certainly don't have to make it as nice as the print face ones. Okay? Why do we use sigma? Okay? This is silly. We use sigma because sigma is the Greek letter S, and summation starts with the letter S. That's the only reason why we use that symbol. Okay? So it's an S. It stands for summing things up. Okay?
A bunch of mathematicians wanted to be fancy.
Yeah. Okay. By the way, someday if you go on in math, you'll see product notation, and product starts with the letter P, and so we use the symbol pi, a capital pi, not the curly one, a capital pi for product notation. Okay. So just to give you a sense of silliness. All right. Now, for those of you who've written some computer programs, this part's going to seem a little intuitive. Okay. We've got this summation notation. Okay, this sigma stands for add them up. We're going to add up a bunch of things. Well, the first thing we should ask is, where do we start adding from? And so that's what, well, actually, before we even do that, this I here is our counter. Okay? For those of you who've written a computer program, the word counter may make sense. If not, what we'll use in math is we'll call it the index. Okay? All we're doing is we're taking a long string of things and we're indexing it. Okay? We're applying an artificial ordering system to it. Okay? We're indexing it. All right? So this is the index or the counter, and this is the start value for our counter. That's the start value for our counter. This is the stop value. Then what are we going to add up? We're going to add up that's something that depends on some formula of our counter. So this is some formula involving I. And let me not use I, let me say the counter. Because in different problems, we will use different letters to denote our counter variable. Folks, it is really important that you spend a little bit of time getting comfortable with this. Okay? I know the truth is that some of you are going to see, we'll work with summation notation for the first two sections, then it'll kind of disappear in the background, and then come the test, you'll look at this, and your eyes will go see just one big monstrous mess, and you'll go, oh, I don't know what that is. Okay? So spend some time with it so you get comfortable. But then also, if, there are times when I'm looking at a monstrous summand in a math book, I don't know what it represents, so I just start writing out some of the terms of it until I start to notice the pattern that the author condensed into that summation notation. Okay? So remember, at all times, this is actually, whether you believe it or not, meant to make your life easier. Okay? So if you're ever confused, go ahead and unpack it. Pretty soon after you've written out 20 terms of it, you'll say, wait a minute, there's an easier way to write this. I'll write it just like this. Okay? All right. So let's go ahead and get started. We'll do this first one together. Okay? So here I've got a summand. It means add up a bunch of things. What am I going to be adding up? I'm going to be adding a bunch of 2 times a number plus 1. I'm going to repeat that operation, adding it each time. Okay? So my index here is I, and where am I starting this at?
4.
When I is 4. So the first entry looks like 2 times 4 plus 1. We have now written out the entire formula where I is 4. Then we put the plus sign that the summand represents, and we move our counter value up 1. So now who is I going to play the role of? 5. So this next one is 2 times 5 plus 1. Okay? We've written out the entire formula that we were taking the summand of, playing with I playing the part of 5. We add 1 to our counter, and we repeat. Okay? When do I stop this?
7.
When I becomes 7. So here's the last entry. Okay? Yeah.
So if we start at 4, wouldn't we assume that we're doing like the left point?
Oh, so careful. At this point, if you've seen some more of the story, at this point, this summand is just an exercise. It's not being, we're going to eventually use, to Tyler's question, we're eventually going to use summation notation to express these sums of rectangles. Yeah, so we're getting there. Right now, we're just playing with this. We're just trying to get used to what is this crazy looking sigma thing. Yeah, great question. Okay. So help me out, folks. I think we get 48.
Yep.
Okay. All right. So I would like you to now, in your groups, do them in this order. B, C, then E, and then do D. Okay. I don't know why. Someday I'm going to switch these two around. Okay. So do B, then C, then E, and then if you feel like it, go back and do D.
Is that L times L? Is that L
Yep.
times those two parentheses?
Yes, yes, yes. So inside the formula for L, you could have whatever operations you want. Multiplication, powers, factorials, square roots.
You said B, C, and then D?
Let's just do it like this. 1 times 2 times 3 plus 2 times 3 times 4 plus 2 times 4
Oh, it's
times
like
5.
this minus this and this.
We do an N, right? So,
We don't know what N is.
exactly.
So although this does represent some compact idea, we can't actually write it all out without knowing what N is.
So what would we do?
Well, just what I did.
So you just like, okay, here's the start and then
Yeah.
question mark.
Yeah,
Okay.
yeah, yeah. Because eventually we're going to vary N. We're going to vary that upper limit. What do we get for this for E, folks, if we actually crunch the numbers?
36.
Yeah, I think we get 36. Adding those up. Remember that, because we're going to need that for another problem. Okay, folks, I am very unconcerned if you get hung up on D. D will not show up on a test, but I just want to show you how this summation notation can be built inside of itself and get more complicated, because eventually you're going to need this. Okay? If you go on to take Calc 3, or if you go on to take linear algebra, you'll be using summons like this. Okay? So let's go ahead and write out the, so this is how I'm going to do this, folks. I'm going to show you sort of the, this is going to look a little bit messier than it needs to be. I'm going to show you one way that is, although it's messy, it's the most intuitive. And then I'll show you a different way to write it. Okay? So the first way to think about it is, I'm going to start off with j being 2 and k being 6. Now, working inside of this summand here, I'm going to keep j stuck at 2 while I run through this summand. So then I'm going to tick up k by 1, and so I've got 2 times 7. Okay? Now I'm at the top of that, I'm at the end value for that sum, and so then I start over with j, and I tick j up 1, and I reset k. And then I've now exhausted the inner summand for k, so then I tick up j one more, and I reset k back down to 6. Okay? We've got a nice little mechanical procedure spelled out in a very compact way. Okay? Remember, folks, and I'll say this again for all of you, especially if you go on and take more math classes, notation is meant to make your lives easier. If you're not getting the notation, you need to stop using it, write it out in longer form for a while until you get a little bit bored with it, and then say, boy, I wish I had a more concise way of writing this. Then you're ready to use the new notation. Okay? All right. Here's another way to look at this one. Okay? Another way to look at this is to call this the summand from j equals 2 to 4 of, and then inside of here, I'm just going to do j times 6 plus j times 7. You see what I did there? I went ahead and evaluated this sum right here, just leaving that as a j, and then expressing this as a 6 plus 7.
Get a little scrunched in there, but
Yeah, I'm sorry, that's
so
hard to
it's
read. This is
4.
j equals 2 to 4 of j times 6 plus j times 7. Where did that j times 6 plus j times 7 come from? I evaluated this right here, just leaving that j without substituting anything for it. So this piece right here is this piece right here. Okay? But then we could go ahead and go one step further, and we do sort of a distributive. This is mimicking your distributive property in a lot of ways. And we get 2 times 6 plus 2 times 7, and then plus 3 times 6 plus 3 times 7 plus, now I'm definitely out of room, 4 times 6 plus 4 times 7, which is grouped the same way, but it's kind of just a little bit different way of thinking about it, which is, I think, in some ways easier as time goes on. Yeah, Maria?
Would you simplify what's in the parentheses, j times?
Oh, yeah, great. Yeah, so there's many properties you can use here. What is j times 6 plus j times 7? It'd be 13j. Yeah. And then you could go ahead and work with it like that. So yes, in fact, I should have seen that. Yeah, that's a great way to do it. Okay? So there are many ways to do these. Okay? And because really summands are just addition, you have lots of properties of multiplication and addition combined together. There are lots of ways to do these. Okay? All right, so again, I'm not gonna give you one as hard as D, but I just wanted to show you that because if you go into any other classes, you're going to see double summands. Okay? All right.